Hello, welcome to our study of carbonyl compounds. What are carbonyl compounds? Well, the carbonyls are said to be compounds that have this functional group, C double bond O. So any compound containing the C double bond O is a carbonyl. However, if we could give meaning to this term, carbonyl compound, like very strictly, there are two groups of organic compounds that are regarded as the main carbonyl compounds. We call them alkanals and alkanones. As you may be well aware, these compounds are otherwise called aldehydes and ketones. So aldehydes and ketones are the main carbonyl compounds. And then from the basics of chemistry, we remember that every carbon atom in an organic compound is supposed to be surrounded by 4 bonds, like that. So that 2 bonds are formed with oxygen already, and then we have 2 empty spaces. So what occupies those empty spaces is what determines whether our carbonyl will be an alkanal or an alkanone. In other words, if we have this, let's look at these two now. If you have an alkyl group here and another alkyl group here, or even aryl groups, then what you are dealing with is an alkanal. In other words, the carbon bearing the oxygen, that's the carbonyl carbon of an alkanal, does not have any hydrogens attached. But the carbonyl carbon of an alkanone has at least 1 hydrogen, which could be this way, so that the remaining position here is occupied by an alkyl group, or both of them are occupied by hydrogen. But that happens in only one case. Yeah, when you have the simplest alkanal called methanal. But apart from methanal, in all other alkanals, this is R. So it means therefore that the general formula for alkanals will be RCHO, whereas the general formula for alkanones will be RCOR. So those are their general formulas. Now moving beyond the general formulas, it may be important for you to know that alkanals usually have higher boiling points and higher melting points than their corresponding alkanones. What do I mean by corresponding? By corresponding, I mean things like propanal and propanone, or butanal and butanone. So those are corresponding alkanals and alkanones, and usually for them, the alkanal takes the day. It has the higher boiling point. Then let's try to look at this in another way. Let's say we have a carbon chain like this. Look at this carbon chain. That chain contains 6 carbons. Now, if we were given double bond O and asked to place it on one of these carbons, then we'd have 6 options. You can place it on any of the 6 of them. Now, if you place it on this first one or on the last one, why am I calling this last now? Just because that is first. Otherwise, if you bring that double bond O here, this guy becomes first and that becomes last. So any of those 2 positions could be called first or last. So we could just call them the first carbon and the last carbon. Now, when your double bond O is on any of them, what you have is an alkanal. But if your double bond O is on any of these, we say what you have is an alkanone. So the position of the double bond and the O, oxygen rather, is what determines whether this will be called an alkanal or an alkanone. So as it is now, if I leave the double bond O there, because there are 6 carbons here, I would want to say hex. So hex stands for 6 carbons. All the carbon to carbon bonds are single. So I would love to add an, as though it were an alkane. They are the ones that are saturated. So we have hexane. And then because it's an alkanal, look at the word alkane. How does an alkane resemble an alkanal? The E appears to have changed to Al, unlike in that case where the E has become on. So that if I have my double bond O there, I'll call this compound hexanal. If I shift it to the next, it becomes hexanone. To this one, hexanone, 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 hexanal. So alkanals have their double bond O at the extremes. Then again, it's possible for an alkanal to have both extremes occupied like this. Such compounds are called dials, and we won't need to indicate position of the double bond O in that. I will just call this compound hexane dial. So it's a dial. I don't need to say 1,6. It couldn't have been any other numbers. Remember, the double bond O has to be at the extremes for us to have an alkanal. So in a dial, we have double bond O at the extremes. Then in compounds where you have double bond O in between, maybe two, more than one now, you could actually have what we call a diketone or dione. So diones are also possible. Having said that, it may just be time for us to talk about how alkanals and alkanones are obtained. What reactions give us alkanals and alkanones? Number one reaction is redox. Redox. And what do we mean by redox? Reduction and oxidation. Now for alkanals, we can get them from primary alcohols. How? By oxidizing them, or we get them from alkanoic acids. How? By reducing alkanoic acids. So alkanals can be obtained from primary alcohols by oxidation or from alkanoic acids by reduction. This is an old story. We talked about it in the alcohol videos. So just in case you're not familiar with this story, you could watch any of the alcohol videos for the details of this. Then we also said in that video that for alkanones, when secondary alcohols are oxidized, they become alkanones. So alkanones can be prepared by oxidation of secondary alcohols. Like I said, all this has been discussed in the past. So that we look at a second way of obtaining carbonyl compounds, and it is ozonolysis. Ozonolysis. We discussed this also in the alkene videos. But just in case you can't go to the alkene video, I'd like to tell you that if you have an alkene, let's say R, C, double bond C, then R, and then R, then down here R, and this alkene is treated with ozone, with CCl4. CCl4 is tetrachloromethane, and in this reaction, it functions as a solvent for the alkene. So the alkene is dissolved in tetrachloromethane, and then ozone is bubbled into it. That is ozonization. That process will give a product called an ozonide. Now, in the presence of water, that ozonide breaks down in what we call a workup. But for the purpose of making carbonyl compounds, we will choose the type of workup we call reductive workup, which is workup that involves the presence of zinc. So it means that after water or ethanoic acid, any of them can be used as an oxygen acceptor for this reaction. After it has broken down our ozonide into two halves, itself, that's the water now, becomes hydrogen peroxide. And that's why this zinc should be there to reduce the hydrogen peroxide so that it does not tamper with any of our products. But please, under exam conditions, you may spare yourself all of those details except you're expected to tell them. Otherwise, under exam conditions, just know that for an alkene given to you like this, undergoing ozonolysis, you can draw your two products easily. Just cut this alkene along the double bond like this. You'll get two halves, right? Give this half oxygen, give that half oxygen. The resulting structures are your two products, especially for cases involving reductive workup. So for this alkene, let's say we call this R1, R2, R3, R4. My products would be R1C double bond O, R2, plus R3C double bond O, then R4. So if you look at what has happened there, the alkene has truly been split along the center, and then the resulting halves have been given oxygen. So in a real life situation now, if we're given an alkene drawn this way, Let's say we draw an alkene this way. We put a CH3 there. Okay, so look at this alkene. If we were to name it first, we'll call it 2-methyl. This is 2-methyl now, but-2-ene. Now this 2-methyl but-2-ene, if it were treated with ozone and then it were made to undergo, that the product from the ozonide were to undergo reductive workup, like moving this entire arrow to that side, and I'm asked to produce or write the products, I'll simply cut this in two. It means that from this first half I'll get CH3, CH, and then half the double bond. That's what you're seeing there. So I'll give that oxygen and I'll call that compound ethanol. Why is it ethanol? Alkanals are RCHO. And this RCHO, this alkanal, has how many carbons? 2. So it is ethanol. Then from this side, what do I get? I get CH3, I get a C, I get another CH3. What does that mean now? CH3 bonded to C, and that C is bonded to another CH3, beg your pardon. Then this double bond I can put here and then add what to it? Oxygen. This is propanone. Propanone. If you check, it matches the formula that we talked about before, which is RCOR. So RCOR is propanone, or CH3COCH3 is propanone, whereas CH3CHO is ethanol. So by this, I am able to make alkanals and alkanones, ozonolysis. Beyond ozonolysis and redox, which are like two ways of making alkanals and alkanones generally, there are some methods that are specific to alkanals and alkanones. Let's see maybe one or two of each of those methods. This next one is partial reduction of RCOCl. RCOCl is the general formula for a group of compounds we call acid chlorides or acyl chlorides. So acyl chlorides or acid chlorides are one of the carboxylic acid derivatives. When those compounds are reduced partially, if they were to be reduced completely, they'll behave like the acids. In fact, generally they behave like acids. You know, primary alcohols, when oxidized, will give what? Alkanals. Then finally, alkanoic acids. Then when acids are reduced, they become what? Alkanals. And finally, primary alcohols. So same way acids can be reduced to alkanal first before primary alcohol, that's how their derivatives like this one can be reduced to alkanal before alcohol. So specifically for these ones, they have that ability to do that two-step reduction. So we can carry out partial reduction of an acid chloride, and it will resemble partial reduction of an acid in that it will give us an alkanal. And to achieve that, we are going to do this RCOCl plus H2 in the presence of PD and S. PD is palladium, that's the catalyst we are using, and then the S there is a poison. It's a poison, that's powdered sulfur. Powdered sulfur is a catalyst poison. So it means that hydrogen is going to be used for this reduction, and that will be the catalyst, but the catalyst will be poisoned, so that this reaction just goes halfway and stops. So that we are going to get our product as RCHO. And what is RCHO? That's an alkanal. So alkanals can be made this way. See one example. Let's say I write CH3COCl plus H2, then in the presence of palladium and sulfur. I'm going to get CH3CHO as main product. So in this case, ethanol chloride has been converted into ethanol. This method of reducing acid chlorides partially using hydrogen, a palladium catalyst, and poisoned with powdered sulfur is called the Rosenmund reduction. We call it the Rosenmund reduction of acid chlorides. So Rosenmund reduction of acid chlorides involves reducing acid chlorides halfway or partially using hydrogen and then a palladium catalyst and in the presence of sulfur. So this is one way of getting alkanals, just alkanals. This method cannot be used to make alkanones. But just in case you want to make alkanones, then you could think of another reaction named after two people. We call it the Friedel and Crafts acylation. Friedel and Crafts acylation. The reaction is called acylation because by the end of that reaction, an acyl group would have been introduced into a certain organic compound. Now, what is acyl? Acyl is RCO. We know that R is alkyl, and C is carbonyl, so that the acyl group is like a combination of what now? The alkyl group and the carbonyl group. So some pick their A, their C, and their YL from there to say that's an acyl group. So an acyl group is like an alkyl carbonyl group, RCO. Now in this case, the Friedel and Crafts acylation is a reaction of benzene. So it means that the initial substrate here will be benzene. Now if benzene were to react with RCOCl in the presence of a trihalide, let's say aluminum catalyst, or aluminum chloride as catalyst now, we are going to get as product, this is substitution reaction. Substitution means that something is going to leave this our benzene and something else is going to replace it. Of course, what will leave our benzene is hydrogen. But what do you think will replace it from here? Acylation. So it's the acyl part that replaces it. So that our product here will be drawn as the benzene ring, and then on top of that we have COR. That's acyl. So imagine that I were to carry out this reaction using CH3COCl as my acid chloride reacting with benzene in the presence of aluminum chloride. It means that this product would have been like this. Yeah, it would have been like that because if you compare these two, you see that R is CH3. And since R is CH3, it means going to that side, R also becomes CH3. This kind of compound is called an aromatic ketone. Aromatic ketone or phenone. So why is it called a phenone? It's called a phenone, please, because this is the phenyl group and then that's the ketone group. So phenyl ketone, condensed together, phenone. And then also, it is called an aromatic ketone because the carbonyl group CO is directly attached to an aromatic ring. It is directly attached, which means if we have something like this, look at this compound now, CH2, then CO, and CH3. This is also a ketone, but this ketone is not aromatic. It is not aromatic because the C double bond O is not directly attached to the ring. Instead, it's attached to a carbon atom that is attached to the ring. So for an aromatic ketone, the C double bond O, that's the carbonyl group now, must be directly attached to what now? The ring. This compound we are looking at is called acetophenone. Acetophenone. So acetophenone is a phenone. It is an aromatic ketone. Aromatic ketones are made this way. There's one last reaction I'll show us under preparation of alkanones. After that reaction, I'll tell us about the reactions that alkanals and alkanones undergo. Very interesting reactions, including acetyl-ketal formation, as well as the aldol condensation and the Cannizzaro reaction. All of those are in store in subsequent alkanal-alkanone videos. I'm hoping to make the videos 3 in number. So 3 or 4 videos on alkanals and alkanones, and we'll be done with their story. But for now, let me show you a last reaction. This last reaction is a reaction of alkanals and alkanones that we appreciate so much. We love it so much because it gives us one reaction or one product, one type of alkanone that is not very common, what we refer to as the cyclic ketone. So this is one way of getting cyclic ketones. So it's a very important reaction, like I said. Now this reaction involves heating. And what are we heating? The calcium or barium. You remember calcium and barium are both in group 2A. So the calcium or barium salts of dicarboxylic acids. So if we have a dicarboxylic acid and then we take its calcium or barium salt and we heat it, we get a cyclic ketone. See an example. If I write COOH, then CH2, let's say bracket 6, then COOH, this compound will be called heptane dioic acid, or sorry, octane dioic acid. Let's not go very far. Let's say we use 5. Beautiful. So CH2 means CH2, CH2, CH2 in 5 places. Then there are 2 other carbons here. So we can call this one heptane dioic acid. So heptane dioic acid is here. Now if I were to heat that acid, so this is heat, in the presence of calcium oxide or barium oxide, the fact is that that acid will form its calcium or barium salt, which will then be decarboxylated. Decarboxylation has to do with removal of carbon from a compound, usually in the form of CO2, carbon dioxide. So one carbon atom will be lost from this reaction. That's what I'm trying to say, that the reaction will involve decarboxylation. And that means that the final product will be 1 carbon less than this initial material. So since this initial material is a hept that has 7 carbons, we expect that the final material will have how many carbons? 6. Yeah, we draw the final material like this. That compound is called cyclohexanone. And then of course you have your water and you have CO2. You can leave it at that. So this is cyclohexanone. Cyclohexanone is a cyclic ketone. Now cyclic ketones are not the same as aromatic ketones. You remember we saw aromatic ketones a while ago. Let me show you something about the aromatic ketones. We draw them like this. In an aromatic ketone, the carbon of the carbonyl group is not a member of the ring. See the members of the ring. See all 6 of them. None of them is bearing the oxygen. It is an external carbon that bears the oxygen. But in this case, of the 6 members of the ring, 1 of them bears the oxygen. So this type, where one of the members of the ring bears the oxygen, is called a cyclic ketone, whereas that is called an aromatic ketone. So if you were to use another case, let's say we have COOH, this time we have CH2, let's say 4, then COOH. This will be called hexane dioic acid because all the carbons here are 6. And then in the presence of barium oxide and heat, what do we get? 6 will become 5. So it means I'm going to draw my product like this. And I'll call that product cyclopentanone. Cyclopentanone. So that is it. This is the preparation of cyclic ketones, starting with what now? Dicarboxylic acids, and then heating them in the presence of calcium oxide or barium oxide. So we just described the reaction as a decarboxylation reaction. We say decarboxylation of the calcium or barium salt of a dicarboxylic acid. That would be all for this video. We have prepared alkanals and alkanones. But what reactions do they undergo? The next video will tell us. Before then, remember that you can watch more of this on Dr. Quinty. Just search DRQUINTY on YouTube. So go on YouTube, search DRQUINTY. Remember to like, remember to subscribe, and then remember to share so that your friends enjoy what you are enjoying. Thanks for watching.